In this video, we want to study the roots of equations and how they are related to their coefficients. To begin with, let's start with the quadratic equation. If this equation has roots alpha and beta, then alpha plus beta is minus b over a, and alpha beta is c over a. And I'm quite sure you somewhat know the reason why. In any case, let's do a quick recap. From this equation, if I were to divide throughout by a, assuming that a is not 0, I'll get this equation. At the same time, since alpha is a root, x minus alpha is a factor, and x minus beta is also a factor. Put together, I can arrive at this equation, which when expanded, I'll get this. Then what you do from here is, you want to compare the coefficients. You want to compare the coefficient of this equation with the coefficient of this equation. By just simply comparing the coefficients, you will see that alpha beta is indeed minus b over a, and alpha beta is c over a. For a quadratic equation, we can see from the last equation that actually the equation can be described as x squared minus the sum of the roots x plus the product. So this equation that we had from the last equation in the earlier slide tell us that if we want to reconstruct the equation, we can simply reconstruct it by finding the sum of the roots and the product of roots and putting them into this expression here, we get the equation. Bear in mind that this is a minus and this is a plus. So it's x squared minus the sum, x plus the product. Such expression is very helpful for us to reconstruct the equation if you know the roots alpha and beta. So what happened here is we want to extend the same idea to the higher order equations such as cubic or quartic and higher order equations. And what we want to study about this equation is we want to establish the relationship between the coefficients and the roots and how we can reconstruct an equation given the roots. So for cubic equations, if this cubic equation has roots alpha, beta and gamma, it can be shown with steps like what you saw earlier for the case of the quadratic equation, that the sum of the roots is this, and the sum of the pair products, I call this the pair products, 2 by 2, right? 2, 2, 2. The sum of the pair products turn out to be c over a, and then finally the product of all the roots is minus d over a. I want you to realize that actually it goes negative, positive and negative again. Can you see? Negative b over a, positive c over a and negative d over a. Negative b over a, positive c over a and negative d over a. And now we are writing the same expression is to write this alpha plus beta and gamma as summation of alpha. Such a notation used in this topic is used to represent alpha plus beta plus gamma. In the case of cubic equation, summation alpha means alpha plus beta plus gamma. Summation of alpha beta for a cubic equation means this. You want to realize that if there are 3 roots, alpha, beta and gamma, there are only possibly 3 different pairs, and the sum of these 3 different pairs can be abbreviated as summation of alpha, beta, and likewise summation of alpha, beta and gamma. In this case, you may think that this notation is redundant, that summation of alpha, beta, gamma in this case is just only one term. But for consistency, I've written them all as summation. But bear in mind that in the case of cubic equation, this one has only one term. So do note the notation that are used in this slide. And for this topic, you want to know that these are acceptable notations. So once again, summation alpha in cubic equation means this, summation alpha beta means this, and summation alpha beta and gamma actually refers to only one term for the case of cubic equation. And to reconstruct a cubic equation given the roots, if you know that this cubic equation has roots alpha, beta and gamma, you can reconstruct the equation with this x cubed minus the sum plus the sum of pair products x minus the product of roots. You can rewrite this in the summation form as summation alpha beta and summation alpha beta gamma. Once again, this is only one term. Or you could simply just go back to the good old days and just construct the equation as just like this, but you will probably have to expand this whole thing to obtain the equation of x cubed minus something x cubed, something x squared, and then something x, and then a constant. So this is a case of a cubic equation, how we can actually reconstruct the cubic equation given the roots alpha, beta, and gamma. In the case of a quartic equation which is of degree 4, and hence it has 4 roots alpha, beta, gamma, and delta, we have similar results. Summation alpha, in the case of quartic equation, I want you to realize that it's actually a summation of 4 terms, alpha, beta, gamma, and delta, is minus BOA. And in the case of a quartic equation with 4 roots, summation alpha, beta actually has 6 terms. Right? Why 6 terms? Because it's like 4C2, or 4 you choose 2 terms to multiply. So you got 4C2, or in this case 6 terms in the sum of the paired products. And this is COA, and this is the sum of the triple products. In this case, there are 4 of them, and this minus DOA. And lastly, this notation, like the earlier one, actually this notation can be quite redundant because it's only 1 term, but nevertheless, to keep it consistent, I'll just write in summation. And this one is E over A. Once again, minus, plus, minus, and plus. And to reconstruct the quartic equation, similar results is shown here, that to reconstruct the equation with the 4 roots alpha, beta, gamma, and delta, this is the expression. Once again, it's minus, plus, minus, and plus. Or you can actually do it from here. But if you do it from here, you have to do the expansion on your own. So now moving forward, how are you able to generalize similar results for equation of higher degree? Like for example, if you have an equation of degree n, you have x power n here, how can you extrapolate what you learned for quadratic, cubic, and quartic to also cover the case for the higher order equation? You can try to extrapolate your thoughts a little bit from here and more or less guess what's going to happen. Okay, in this topic, having known all the equations, roots, and their relationship with the coefficients, in order to do some of the arithmetic in this topic, you need to know some simple identities. This is the first one, and this is easy. This is another one. This for summation alpha cube plus beta cube. This is another one. And then you can actually deduce this one actually from here by replacing all the beta as minus beta. And then for alpha square plus beta square plus gamma square, it can be proven that it's actually this. So this relationship is used quite often to find the sum of the squares of the roots. Now, if you have 4 roots, you want to know that this result is quite similar to the last one you saw, and this becomes sum of the square minus twice of the sum of the paired product. And what's happening here is this statement is actually true for even higher order. For any order, whether degree 2, 3, 4, 5, and so on and so forth, the summation of the square of the roots can be proven to be square of the summation of roots minus twice the sum of the paired products. This statement is a general truth for all equations of any degree. Of course, I mean polynomial equations. Okay, now that you have learned quite a fair bit, it's now for me to pose some small challenges to you. So, small challenge number 1. Suppose you have roots alpha, beta, and gamma. Supposedly this equation has roots alpha, beta, and gamma. There's obviously a mistake here. Where A is not 0. I meant to say when A is not 0. Don't have D here. Alright? The question I ask you is, in 3 seconds, can you write down the equation that has roots? So I'm going to count down. 3, 2, 1. The answer, please. Ta-da! So if this equation has root alpha, beta, and gamma, then an equation with this as roots will be like this. What do you notice about this equation as compared to the one above? you realize that the coefficients are just reversed. So if these are the roots of this equation, then these are the roots of this other equation. This small change number 1. Small change number 2. If you have a cubic equation with this as roots, we want to have a cubic equation where these are the roots. And you have two choices to pick from. Do you think it's A, this, or do you think it's B? Once again, I'm going to count to 3. 3, 2, 1. What do you think is the answer? Is it A or B? And the answer is actually A. Right, it's actually A. Why is it A? A quick way to see that it is actually A is like this. Because alpha is the root of this equation, you can put alpha into all these x's and you get 0. So between the two equations, if now I'll put alpha plus 1 into the x's, I must also get a 0, right? And if I put alpha plus 1 into, say, the first equation, I'll get alpha plus 1 minus 1, so just alpha cubed, alpha square, alpha. And therefore, I will get the same expression that I would have if I put alpha into here. Right? But if I put this alpha plus 1 into the second equation, I would not be sure that it will become 0 because it doesn't match what I will get if I put alpha into here. So for this reason, you can actually guess that A is actually the correct answer. But of course, when you read up the notes, you should read up more about this kind of arithmetic in the notes where we use so-called substitution method to derive a new equation from an earlier equation, all because the roots of the first equation and the roots of the second equation are related. So when you read out the notes, you want to look into example that uses substitution to derive one equation from the other. So with this, we have come to a conclusion of discussion from the notes on roots of equation and how they are related to their coefficient. Thank you.